Assalamu alaikum, everybody. Students, today we will be discussing E1cB reactions. First of all, what are E1cB reaction? This reaction is due to the presence of anion stabilizing groups in the substrate. At first glance, it seems just similar to the E2 and E1 mechanism, but it's somewhat different from both the E1 and E2 reaction. It's an elimination reaction which is catalyzed by a strong base like potassium hydroxide, so it looks like an E2 reaction. But as in E2 reaction, there is first the elimination of the X group. Here it's not the case. In this, the leaving group is an hydroxide, which we categorically and truthfully stated cannot be a leaving group in E2 eliminations. The E1cB reaction is just like an Sn2 reaction, but the difference is that there is an anion formation prior to the loss of leaving group. This reaction is possible if there is a group present that can stabilize the negative charge. The basic difference in the elimination reactions and the E1cB reaction is the presence of a carbonyl group or any other negative charge stabilizing group. The negative charges are stabilized by conjugation with carbonyl groups. A proton adjacent to carbonyl group is the acidic proton. The proton that is removed in this elimination reaction is adjacent to the carbonyl group and is therefore also slightly acidic. This means that the base can remove it without the leaving group departing at the same time. The anion that results is stable enough to exist because it can be delocalized into the carbonyl group. Here, if you see, this is the reaction and an elimination product. How this reaction proceeds now? This proton, this is the acidic proton. It's first removed by the base and we get an anion. This anion is adjacent to the carbonylic function and then it is delocalized with the adjacent carbonyl functionality. Now the second step is the elimination of hydroxyl group. You see here this double bond is migrated here and the hydroxyl group is removed and we get this elimination product, this one. So this is the mechanism of the E1cB reaction. The loss of hydroxyl and the formation of double bond is the rate determining step of the elimination, E1cB elimination. The elimination is unimolecular and so is some kind of E1 reaction. The leaving group is not lost from the starting molecule but from the conjugate base of the starting molecule. So this sort of elimination, which starts with a deprotonation, is called E1cB. CB stands for conjugate base because the leaving group is lost from the conjugate base. So this is why it's called E1cB reaction. The hydroxyl is never a leaving group in the E2 elimination. It can be a leaving group in the E1cB reactions only. The establishment of conjugation in the product also assists the loss of hydroxyl. This is the mechanism. Like for other molecules, first the acidic proton is removed. It's a deprotonation step. This is then stabilized anionic intermediate, and this one is the rate determining step. Similarly, in this molecule, firstly the proton is abstracted, and then we get this elimination product. The rate determining elimination step in an E1cB reaction is unimolecular, but it is not a first-order reaction. The rate is also dependent upon the concentration of the base. As the unimolecular elimination involves a species, the anion, whose concentration is itself determined by the concentration of the base. Equilibrium we just have been discussing. Using the following general E1cB reaction, the concentration of the anion can be expressed as shown. The base hydroxide appears in the rate equation does not mean to say it is involved in the rate determining step. Increasing the concentration of base makes the reaction go faster by increasing the amount of anion available to eliminate. So the rate of E1cB can be expressed as like this one. And this is the rate of the E1cB, constant concentration of the substrate and the concentration of the base. Come to the competition between substitution and elimination reactions. There is some similarities between the elimination and substitution. The conditions that favor E2 reactions also favor the Sn2 reactions. The conditions that favor E1 reactions also favor Sn1 reaction. First, that which conditions can favor the Sn2, E2 or Sn1, E1 reaction. If the halide is primary, only the Sn2 or E2 reactions are possible. If the halide is secondary or tertiary, both Sn2 or Sn1 are possible depending upon the condition of the reaction. The Sn2 or E2 reactions are favored by high concentration of a good nucleophile or strong base and polar aprotic solvents, while the Sn1 and E1 reactions are favored by poor nucleophile or weaker base and polar protic solvents. Primary halides generally undergo substitution. Although if the halide or the base is hindered, elimination is possible. And elimination is also favorable if we apply heat or high temperature. The secondary halides are more difficult to predict because it can undergo Sn1 or Sn2, or it can undergo E1 or E2, depending upon the different reaction conditions. The stronger and more hindered the base, the more the elimination product is produced. The higher the temperature, the more elimination product is produced. The tertiary halides will never undergo Sn2 reaction. Only possibility is the elimination reaction. This is like here you see this molecule. This is a secondary halide, and here we have a protein solvent, and this is a bulky base. So Sn2 product will be obtained. But if we have a protein solvent and comparatively smaller base, stronger one, so then E2 product is the more dominant one. There's a possibility of Sn2 product also, but it is only 25%. Most will be the E2 product. But it shows that there is a strong similarity between the E2 and Sn2 reaction. Strong nucleophiles favor substitution, while strong bases favor elimination reactions. Sn1 and E1 reactions both proceed through carbocation. They have the same rate determining step. Primary halides do not undergo either Sn1 or E1 reaction. There are a lot of similarities between the Sn1 and E1 reactions. First is the formation of carbocation. In both the cases, the first step is the formation of carbocation. And the second similarity is that the primary halide in both cases doesn't undergo neither Sn1 or E1 reaction. For secondary and tertiary halide, raising the temperature increasing the elimination product. The higher the temperature, the more will be the elimination product. In the E1, the first step is the same as the Sn1 mechanism. Here you can see this is the molecule, the substrate or base, and the cation formation. The cation is formed, and now it can go both the way. It can give an E1 elimination product like here, alkene, or it can give a substitution product here. Propyl bromide has been formed. This is a substitution product, and here it is an elimination product. The E1 pathway competes with the Sn1 pathway. This is the 2-bromo-2-methylpropane. The first step is the same. It is the formation of the carbocation, a tertiary carbocation. Now, both the reactions are possible depending upon the conditions. E1 is possible, and we get 20% of 2-methylpropene, or Sn1 is possible, and we will get 80% of 2-methoxy-2-methylpropane here. The steric bulk favors elimination reaction. If there is steric hindrance, bulky groups present, so then the formation of elimination product is more favored. Sn2 substitution on a tertiary carbon is not possible. So therefore the only choice remains, that is the E2 elimination. But with the E2 elimination, the E1 elimination is also possible in the tertiary carbons, the presence of tertiary carbons or tertiary compounds. All these materials, these were taken from Organic Chemistry by Claydon and Organic Chemistry by Paula Bruce, mostly from Claydon and some from the Jerry March. Thank you very much for your patience. Thanks a lot. Thank you.